Okay, welcome back, everyone. Today, let me just hit so we have a backup. Today we will we have our last regular lecture. So we'll be wrapping up some dimensionality reduction today. That's kind of part of the filter and aggregation piece. And after that, we will be going into text visualization and then finally set visualization. But before we get started, are there any questions about projects or anything like that? Pretty loud. So does it sound better now?
I have a quick question for the README.
Sure.
To what detail do we need to go into our project structure? If, for instance, we stuck to the same structure as we had with the homeworks, having a JS folder, a CSS folder, and figures folder, is that sufficient enough without documentation, or do we need to supply more for that?
Yeah. So basically, if you're like, you should just briefly describe what's going on. If you just use like a pure client side, then this can be very brief, right? But some people are using a server. And then we would need some instructions on how to do that.
Okay, thank you.
Any other questions about the project? I just want to emphasize the importance of the video and of the kind of like the whole presentation piece, because like the video, like if you're doing a great project, we'll be showing the video in class, and you also want to make sure that this is great and you can kind of like use this as a as part of your portfolio, put in your website if you're applying for jobs and so on. So this kind of stuff is quite important. So don't do this in the very last minute and think a little bit about what you want to do in your video. Okay, great. So to recap, last time we talked about filtering and aggregation. And for filtering, we had any kinds of like data-driven filtering. We distinguish between filtering and querying, where filtering is you start with like an overview of all elements, you reduce them. Querying is you start with nothing, and then you submit a query and you get something. And then we talked about aggregation, and in the aggregation, we talked about spatial aggregation, about the challenges we have if you want to aggregate elements on a map, the modifiable aerial unit problem. And like one solution to that was Voronoi diagrams or Voronoi maps, and we looked at how we can do that. And then finally, we looked at clustering and how we can create clusters with a couple of different algorithms, what their properties are, and so on. And now we didn't get to dimensionality reduction. And dimensionality reduction is kind of like the next big thing in kind of like doing aggregation, especially in terms of aggregation for the number of dimensions. Clustering is really useful to group items. You can also use it to group dimensions, but typically clustering is used to group items, whereas this dimensionality reduction kind of tries to like deal with a large set of dimensions and make the stuff that you're looking for kind of like intangible in lower spaces. And so, yeah, that's the point of dimensionality reduction. We want to reduce some high dimensional data sets to a lower dimensional space, and then visualize that lower dimensional space. And the goal of dimensionality reduction methods is to preserve as much of the variation as possible, and then plot this in a lower dimensional space. Like the classic technique that you've heard about, I'm sure, is principal component analysis. And this is kind of like a linear mapping that kind of maps to like multiple principal components by order of variance. And so if you had like a two-dimensional scatter plot, like you can see on the right, we would calculate two principal components. And the first principal component here would be the long arrow you see, like this here. And that is because like much of the variance in this data set is actually captured along that dimension, right? So if you wanted to reduce this two-dimensional data set to a one-dimensional data set using this axis, just using this axis here and plotting like this point here is here, this point, let's say this point here is here, this point here is here, that kind of preserves a lot of the structure of the data set. And so you have to think of this, like if you have a two-dimensional data set, it doesn't make all that much sense to reduce it to a one-dimensional data set, but it's kind of useful to think of this example and kind of generalize it to a higher dimensional data set, right? If I have like 6 or 7 or 100 or 500 dimensions, maybe I can find like a good first or second or third principal component to visualize what's going on. And so here's like a pretty good intuitive example of how principal component analysis works. And I'm not going to go into the math. There's other classes that do this kind of stuff. But I really want you to kind of like understand what's going on behind it. So here I have my two-dimensional data set that I kind of similar to what I showed. And here I have these points, right? And these points, if I put them all on like a nice kind of like on a nice line here, then I can see like this is my original data set, and here I have my principal component plot. Principal component 1 is on the x-axis, principal component 2 is on the y-axis, and you can see the principal components here, and the first and the second as red and green axis in this plot here. And so you can see that by essentially like in this plot, because everything is along a line, almost all of the variance here is captured nicely by the first principal component. But if I start moving it away one of the points, then you can see that I have to kind of like this information isn't contained in the first principal component. It's only contained in the second principal component in that case. And so we can play around with this. We can kind of build up a data set. And then at some point you see like this data set here, for example, doesn't have like all that meaningful principal components anymore. Here's like a 3D example. I have these point clouds here, and I can kind of like show the principal components. What is the first principal component is kind of like this axis through the 3D point cloud here that kind of like makes sense because most of the variance is happening along that axis. The second principal component is this green arrow here. And I think that kind of like a very good example here is this 17-dimensional example. Like we start, this is like a data set of, we have like food preference in like countries of the United Kingdom, England, Northern Ireland, Scotland, and Wales. And we have like how much does the typical person or the average person consume of alcohol, other beverages, meat, cereal, cheese, soft drinks, and so on. And so we can look at this in a higher dimensional space, and we can kind of try to analyze, well, it seems like the Scottish people are drinking more than the Northern Irish. It seems like fresh fruit is more popular in England than in Northern Ireland. So we can kind of like reason about this, but we can also calculate the principal components. And if we do that for the 17-dimensional data set, we very quickly see that Wales, England, and Scotland are fairly similar to each other, but Northern Ireland is kind of an outlier. And so if you look at why might that be, well, we can see that potatoes are much more common, whereas fruit are much less common in Northern Ireland. So they seem to be kind of like slightly the odd bunch amongst the countries among the UK. And if I plot two principal components, I would have something like this. Actually, let me close this. Okay, so principal component analysis is like one simple way of doing this. There's many other multiple dimensionality reduction algorithms. One of them is multidimensional scaling, and that's kind of like more of like a name for a family of approaches. It works based on projecting a similarity matrix, and then you have to ask a couple of questions, such as how do you compute similarity? how do you project the points? And this is what we, like the design critique we did last time, used that kind of method. It used multidimensional scaling to project these points, these points, either philosophers or musicians, into 2D space, and to place the two place items that are similar close to each other. And multidimensional scaling is pretty popular for text analysis. We'll talk a little bit about that later. Like one problem though with all of these techniques is that there's something about it that kind of like, since they're trying to reduce a higher dimensional space and create a lower dimensional picture, there is always error, right? These are not perfect representations. And so if you look at this chart here, this is like a text visualization of dissertation at Stanford. And it kind of like categorizes in this dimension, with this dimensionality reduction method, how similar are the kinds of dissertations to each other from these different departments. And you have things like electrical, mechanical engineering, geology, computer science, petroleum engineering, neurobiology, medicine, and so on. And kind of what's odd here is that it looks like petroleum engineering is actually closer to neurobiology than it is to, let's say, computer science or mechanical engineering or civil engineering, right? And intuitively, that is just not correct. And if we look at this, what's going on here, if we can kind of correct for the individual distances, then we see that it's actually not the case. And so remember that like overall multidimensional, like dimensional reduction with multidimensional scaling tries to do like a global optimization. And if we kind of like calculate the distances to each of these fields one by one, we get a picture like this. And here now we have petroleum engineering. And now the distances between the individual points in the outer ring here are actually not relevant. Instead, it's only the distance to petroleum engineering that we're looking at. And we can see that we have kind of like, this was really just an artifact of the algorithm, right? So petroleum engineering seems to be closest to civil engineering and to aerospace and to aerospace and electrical engineering, and much less close to neurobiology, right? So like you see that this really was a mistake. And so whenever you use it on the dimensionality reduction method, you will have these artifacts. And so before you make any like hard decisions based on such a plot, you have to look at kind of like, is what you're trying to decide actually in the data? And this visualization technique here gets at that. I'm not going to go to it in the interest of time today, but this kind of like visualizes these projections, but it also shows you the error terms, and you can like dynamically correct for them live and kind of like adjust it live. And so that's kind of like a pretty cool technique if you want to play around with these with the errors in these projections. And then another important class, especially recently, are these kind of like fancy algorithmic approaches such as t-SNE and UMAP. You've probably heard of those. And so here's like a three-dimensional point cloud. These are the MNIST digits. And so, or no, this is actually, well, it's actually MNIST digits, yeah. And so what's happening here is this algorithm tries to like does something like for t-SNE and UMAP. It's really important to judge only elements that are close to each, like that are in a group, and not try to kind of like infer. Let's say the red group here is very close to the pink group or to the orange group. And so you can kind of like navigate this. And why do you think this here is three-dimensional? And is like I've always ranted about three-dimensional scatter plots, and suddenly I'm showing you a three-dimensional scatter plot. Does anybody have any thoughts why this is maybe not the worst idea here?
You can sort of do projections to sort of look for almost principal coordinates, maybe?
Yeah, you're on the right track. Like, one of the problems with 3D scatter plots is that it's really hard to read labels, right? And to get occlusion and to read precise values. But these precise values in these kinds of projection techniques are meaningless anyways, right? What you really want is kind of like the gist of how do these clusters form. And so here, like it's actually like if you navigate and play with this, you can see these clusters emerge much better than if you just have a static representation, right? So in this case, if you really just want to see these clouds, these clusters, and don't care so much about the values of individual elements and so on, then that's probably a reasonable thing to do. And I just wanted to mention a couple of tools, like if you're interested in t-SNE or UMAP, there's a couple of tools out there, mostly by the Google Brain or Google Big Picture group, that have these interactive tutorials on how to use t-SNE and UMAP. This is one example. This is linked. The slides are already in the website, so you can like follow that if you're interested and play with it. And they kind of like give you some different kinds of input patterns, and then do t-SNE on it, and then you can play around with some of the parameterization so that you kind of develop an intuition about how to interpret t-SNE plots. And similarly, UMAP is like another like mathematically very fancy technique that has similar properties to t-SNE. And they like, here is an example of one of these like explainer articles about building intuition about using UMAP. And so in summary, UMAP and t-SNE are pretty good at, if you have some kind of like a very high dimensional data set, as you would use it for your machine learning, and to kind of like see some structure and start to kind of like understand what's going on before you like do your actual learning or your actual predictions. And then you can do things on top of multidimensional scaling. So for example, you could do multidimensional scaling for time series data. So here we're looking at Wikipedia articles about how they change over time. And so two articles that are like almost identical, just like a spelling mistake has been corrected, would be essentially exactly the same. So they would end up in the same point. But as articles are edited heavily, they move away further, so the similarity changes. And so you can see how, for example, like the Wikipedia article for chocolate, kind of like how that evolved. And so here we can see kind of like an edit war. We see that like we had this status, like this status here, and then somebody changed to do that, and then it was changed back, and then it was changed back again. And so we have like a couple of iteration of that, and we see that there's kind of like this loop here. So maybe somebody has changed this article to be closer to this source here from that point here than it was before. And especially controversial articles, like politically controversial articles, you frequently see these kinds of edit wars, as you can see here for the Wikipedia article for Palestine. Again, there's a link, you can play with these, and it's a pretty cool idea to show this time series data like that. Okay, before I move to text visualizations, any questions about multidimensional scaling or filtering and aggregation in general? Okay, great. So now let's talk about text and document visualization. And so text is kind of like a unique data set. And if you recall, we talked about this in the data lecture. Text is not like strictly structured. It's pretty abstract, but it's super general, and it's very, very expressive, right? We use text or language to communicate anything that we want. Sometimes, of course, other forms like visualizations are better, but generally, like a language is something that we frequently use, and that is very powerful, and it contains a lot of information. However, text is also challenging because it is very different across population groups. By like, you have different countries with different languages, you have different accents, you have different religions, we have like meanings that play a role, and so on. And so there's like, text isn't quite the same as like a scatter plot, right? A scatter plot is universal, whereas language is very, very cultural. And the other thing that is unique about text or language is that we have linear perception. Like, we can see a picture more or less in parallel. We can spot patterns in, say, a scatter plot in parallel. But language and text is something that we see like in sequence. So you're listening to me speak now. You couldn't hear me speak about 5 different slides simultaneously, but you can see 5 different things simultaneously. And text is fundamentally, it's unstructured, but you have some, or like from a computer science perspective, right? It's not that we have like structured information in a typical text. In practice, it is semi-structured. You have things like headings, you have paragraphs, you have sentences, you have your rules of grammar that you can often infer and you can leverage, and then you have words, and then eventually you have characters and all kinds of other elements that you use, like highlights, to structure text. And so sometimes you can use some of the structured information, but mostly you can treat, like from a visualization perspective, you can treat text as unstructured. And so what you really need to do is first derive some structure. There is, of course, visualization for raw text, and these are some examples that you might be using in your daily lives, right? If you have like, you can think of like having a big page, like front page of the New York Times, as giving you like a text visualization. They're using kind of smart headings, placements, and font sizes and so on to give you an overview of what is like happening in the text below. Similarly, if you are looking at the PDF on any of your computers, you probably have a preview of what would be the next pages so that you can see what's going on. Or if you use like Visual Studio Code, you have kind of like this view on the right where there is kind of like basically unreadable text, but they still show you the whole file to enable you to quickly navigate to different parts of that file. And so there you're leveraging more of kind of like color highlighting. Visual Studio shows you kind of like there's a warning here, or some like you can integrate that with debugging, or you can see some kind of like data, like some structure, like here's a deep nested loop. You can immediately see something like that, even if you can't read the text. And so you can visualize raw text, but it's usually not all that exciting. And historically, there have been approaches like this. So this is like the document lens, which is like an old paper from 1993. It's kind of like one of the early text visualization papers. But you could also do things like variable scaling when you search, like when you or kind of summarizing text interactively, like you can see here on the right. And so this is also still raw text visualization. But mostly what you want to do is you want to kind of like infer some structure about the text. So if we have unstructured text and the text unstructured text here on the left, we could kind of derive structure in terms of like how many T's are in that word, in these words, how many U's are in these words, how many R's, how many E's. And so if you wanted to like see which letters are most frequently used, that would be an easy way to derive structure. Of course, it's not all that useful unless you're trying to design a game like Scrabble. What instead you usually do is some kind of like smarter ways to extract features. And one simple thing to do would be kind of like bag of words that are simple counts. So if you have, for example, the words princess, dragon, and castle, and then you have two documents, and you can count how frequently do those appear, you can kind of like reason about how similar are these two documents based on how many words they share, especially these kind of like rarer words. Like dragon is not a very common word. Like after removing stop words like the and a and so on, you get a set of words, and then you can use those to give you kind of like a metric about like how similar are, for example, two documents. And then you could use something like this with dimensionality, like with multidimensional scaling, to show how similar are certain documents. And so typically, and as I said in the data lecture, this is kind of like a topic of its own research area and its own lecture, its own class, even at the U. This is all about natural language processing, right? And we typically want to do things like cleaning, sentence splitting, changing to lowercase, stop word removal, stemming words, part of speech tagging, noun chunking, name entity recognition, and then eventually also deep parsing with some fancier methods to understand text. And so these are the kinds of methods that you apply before you can actually do visualization. And of course, like text features are fairly complicated. Toilet out of order, please use floor below could be interpreted in different ways, right? It's ambiguous, or one morning I shot an elephant in my pajamas. How he got into my pajamas, I don't know. Things like that. Like language is ambiguous, and it takes a lot to really understand what's going on. If we kind of like structure text, we have a hierarchy. We start with like letters, words, word groups, sentences, paragraphs, and then go on to higher level elements, sections, chapters, documents, document cluster, corpus, and then corpora. And it's useful to think about, like, usually if you build a text visualization, you want to be in like one of those spaces, but you don't want to do all of them simultaneously. So for example, if you want to visualize patterns and how similar certain patterns are and which patterns are relevant for you, you're kind of like at the corpus or corpus of corpora level. But if you want to see like kind of like what are the words or the style that is being used in poets by poets in a certain poem, then you're kind of like down at the linguistic visualization level. And so you kind of have to pick where you want to like set your focus to create good text visualizations. The like probably most popular word visualization is at this kind of like document level is the Wordle, and that is a very simple visualization. It is just frequency based. It scales words by how often they occur, and then show them like scaled by their frequency. And so you can see an example of that on the right, and then you can vary font type, size, color, and so on. And so there's these visualizations that were pretty popular a while ago. I'm not sure this actually, I didn't try this beforehand. Yeah, it does. So you can create your own worlds. You can paste a bunch of text and then create your Wordle. Many other like visualization tools support Wordles, and there's plenty of visualization like optimization work about Wordles going on. Like how can I place words correctly? How can I create certain shapes and so on? But fundamentally, it's kind of like more of a visualization with the purpose of kind of entertaining and giving like a quick summary, but you're not going to learn a lot of meaning about the text that you're studying by using something like a Wordle. Wordles kind of have their kind of origin in tag clouds. So tag clouds are very similar, but they're just like simpler algorithmically. They use kind of like just a layout and scale, like a linear layout and scale the words by frequency. Wordles instead kind of like do some more fancy placements of the words so that it's kind of like a visually more appealing placement, and they also have more freedom in terms of like showing text at certain angles and so on. And so there's now plenty of approaches to create Wordles in like aesthetically appealing ways. You can like have the Gettysburg Address or superimposed over like an outline of Lincoln and so on. All of this is possible. Another technique is the word tree. And the word tree is kind of useful for repetitive text, such as poems. For example, if you have a poem like, if love be rough with you, be rough with love. If love be blind, love cannot hit the mark. If love be blind. And so the word tree detects these kind of substructures and creates like a representation of these substructures. So the three sentences on the left all start with if love be. And you can see that this is pretty big and bold. And then we have a split into like a single branch, rough with you, and then we have blind, and blind has again sub branches and so on. And so these are fairly simple to create. But it's still kind of sometimes fun to look at what's going on with certain text with certain corpora. So here is an example of I think this is a Shakespeare. Yeah, it's Romeo and Juliet. Yes. And so you can see like if and what are all of the different ways that if is used in as a start of a phrase in Romeo and Juliet, right? And you can see if thou or if you or if I are fairly common structures, but they're by far not unique. Similarly, I did show this example in the data lecture. Phrase nets. Phrase nets have this very simple idea of explicitly creating a simple filter, like you have word 1 and word 2, or like you could say word 1, comma, or word 1's word 2, or something like that, and then you can extract a graph from that. So I showed this example before, like relationships. This is like who beget whom in the Bible. So Abraham beget Isaac, and so on, and you can kind of like reconstruct family relationships from that. More commonly and more general are these kinds of like MDS approaches to kind of like analyze text corpora. So here you use this bag of word approach that I mentioned earlier to project documents with respect to their similarity into a landscape. And then you would expect that similar documents end up close to each other. And so here's just like an example of how this would look like. First, on the top, you have a scatter plot of these kind of like reduced dimensions, and then you can select a subset of these documents and then create a wordle out of it. And then you see that you have, well, on the left side, the cluster here was really mostly about graph drawing, and the right cluster here was really about user interfaces and technology and software and so on. So you can see that you get a bit of an insight into these documents with that method here. And there's plenty of tools out there that do that. Like one popular tool is Jigsaw. Jigsaw kind of comes out of the intelligence analysis niche, and as you can imagine, post 9/11, this whole like research area blew up. Like people wanted to analyze all kinds of email communications and so on, and kind of understand that quickly and derive insights from it. And so you have these tools that kind of like create these document clusters that you can then explore, and then you have some kind of like entity extraction, like individuals on the right here. You see Bill Clinton, George Bush, and Bin Laden, and how they are connected with each other and so on.
This scenario presents an exploration of the 9/11 Commission report using the Jigsaw visual analytics system. Here, we treat each page of the report as a separate document in a collection. Entity identification first determines the people, places, and organizations mentioned throughout the collection. An analyst can explore lists of these entities by type. Sorting each entity list by frequency shows the most common entities of each type. Selecting an entity, such as Osama bin Laden, highlights in orange all entities co-occurring with him on some page. Darker orange indicates a stronger connection. Further sorting of a list by this connection strength brings the strongest connections to the top. Note the strong connections to different organizations, people, and locations. An alternate view of the collection represents each document as a small rectangle and clusters the documents by theme. 3 keywords help communicate the topic of each cluster. Selecting an entity such as bin Laden in one view highlights all documents it occurs in within the other views. Bin Laden is frequently mentioned in the clusters Interview 2004 FDNY and Attacks Operators Taliban. A graph view of the collection depicts entities as small colored circles and documents as white rectangles, all connected through network edges. Here we load and expand the Donald Rumsfeld entity node to show all the documents it occurs in. Expanding each of these documents in turn shows the entities within them. Let's focus on people and organizations.
Okay, I think you get the idea. And similar to that, like, of course, this doesn't only apply to intelligence analysis. You can create kind of like these kinds of overviews for all kinds of corpora here. This is a visualization that shows us scientific papers from 3 different conferences: the Information Visualization, the Scientific Visualization Conference, and the SIGGRAPH, the Graphics Conference. And you can see that like there are certain elements, certain text pieces that are similar to all of these, like method, algorithm, approach, and so on, whereas some other things are fairly unique to a particular conference. So for example, graph edge is very specific to Infovis, whereas topological feature is very specific to SciVis, whereas reconstruction, camera, video, motion, deformation, simulation, force, and so on is fairly specific to SIGGRAPH. And so you kind of get a sense of the different topics that that appear in these corpora. I should have zoomed that in. And then you also can look at these text corpora over time, especially in, let's say, social media analysis. So if you want to, this is an example of a Twitter visualization for a specific event. And so you could say, what are the topics that are emerging and kind of like increasing and ebbing over time? And that's what you see here at the top for a particular event. And then there is like a participant view. There's how many, like these are scaled by how frequently they kind of like mention something in that particular event. And then you have like a photo view and then like a raw data view. And so these kinds of things are like pretty cool to do and pretty easy to do nowadays with the kind of like NLP methods that we have. And so we can get these nice overviews of what is going on in let's say, a particular topic, a trending topic on Twitter.
More and more posting short status updates to digital back channels like Twitter, sharing live impressions during large-scale events. The common interface for following these conversations are text-based lists of tweets. These lists make it virtually impossible to follow conversations and get a general overview of what the back channel is about. With Visual Backchannel, we introduce a new type of interface for following online conversations around large-scale events. The interface provides multiple interactive visualizations that represent important facets of digital backchannels, such as topics, participants, and photos. Topic screens visualize the evolution of topics over time. The more active a topic is, the larger the stream appears. Newest topics are displayed on the top. Participants are displayed in the people spiral.
I think it's fairly clear what's going on here. And then another kind of cool idea is to visualize storylines. And so this is kind of inspired by XKCD, which did like this graph of like how different actors in movies such as Lord of the Rings or Star Wars or Jurassic Park or 12 Angry Men interacted. And you kind of see some kind of like themes emerging from them. And so these, the characters are in immediate proximity if they're co-appearing in a certain scene. And you can see where, like how, for example, Lord of the Rings, there's this kind of like, it's starting to cluster towards the end, but not everybody is always participating in all of the different actions. And people have, based on this idea, have actually developed algorithms to automatically create these kinds of charts from text corpora. And so they do some kind of like entity recognition, and then you have Gandalf or whatever, like locations and so on top overlaid here, and then you can automatically generate these kinds of graphs. And the last technique that I want to show, or the last thing that I want to mention, that visualization is increasingly often used kind of like in NLP to optimize models, but also maybe to kind of like understand what's going on with text. And so as you probably heard, GPT-2 and GPT-3 now, they're kind of like these generative text models that can create seemingly pretty good text. And so one thing that you can do is, like here I'm loading a text that was generated by GPT-2. And so if you read this, the following is a transcript from the Gardens interview with the British ambassador to the UN, John Baird. Baird, the situation in Syria is very dire, and so on. And so you can see this reads pretty good according to a human. But what this visualization here does is it gives you kind of like a color coding for like if I had this word or this sentence, the following, what's the probability that like a machine learning model would pick the next word? And so if the next word, the following word that's appearing in a sentence is among the top 10 values, it is kind of color coded in green. And so you can see that all of these words here are like kind of super expected by this machine learning model. Now let's take a look at if we have a human written article. We can see that there's like much less frequent words that are kind of like suddenly interspersed here. So we have like along the edge of Money Road, right? That Money Road wasn't something that the model was expecting here, or store rods, or something like that. And so if we look at another machine-generated text, we can see that, well, mostly it's within the top 10, sometimes within the top 100. If we look at some academic text, we can see that there are some like likely words, but then there's a lot of words that are very unlikely. And so that's just one way of like, if you want to see, like if you want to analyze whether a text was generated or whether a human wrote it, you could use like a visualization approach with a model like this to see that. And so I find that very intriguing, that you can kind of like spot this without even having to read it, what's going on here. And so a summary like of all of these kind of different text visualization techniques, if you're interested, is on this website. This is like based on a state-of-the-art report, textvis.lnu.se. And we've seen something like this for tree visualization and for network visualization and so on. So you're probably familiar with this by now. So this gives you like a nice overview of what is going on there. This is like a big area, and barely 30 minutes. And so like if you're interested in that, I would recommend that you look at that website here. So any questions about text visualization? Well, if not, I want to go into this design workshop that I announced for today. And so this is going to be a little bit different from my usual approach, because I want this to be a little bit longer and actually have you develop 3 different designs in groups. And it's also going to be like not a standard activity, but it's also going to be the bonus. So you can get like 1% on top of your usual grade. So you could, in theory, get like a more than perfect grade. And so this is going to be about set visualization, which is kind of like the topic of the next section of the lecture. And so imagine like you have like items and then sets. And so item 1 would be an A, item 2 would be an A, item 3 would be an AB, item 4 an AC, and so on. We can visualize something like this as a Venn diagram, right? Like we see that item 3 would be in A and B, but not in C, and so on. And so the Venn diagram is kind of the canonical representation of these set problems. But then it turns out that Venn diagrams are great for 3 sets, but they're really, really hard for more than 3 sets. And so this is kind of a Venn diagram that I always come back to when I talk about set visualization, the banana Venn diagram that shows us the genetic overlap of 6 different plant species. And so this was in a scientific paper that was published in Nature about the banana genome, hence the banana shape in the background. And it's supposed to show you how many genes are shared between the banana and these other 5 different plant species. But it's a terrible visualization. You have kind of like this tiny segment up here, for example, represent 1,151 shared genes. And then right next to it, there's a segment with only 40 genes. And so clearly, this isn't like this violates plenty of visualization design guidelines, right? We like, for example, it violates the lie factor. The data should be proportional to the graphical effect in a chart or in a visualization. That's clearly not the case here. Another example is you have like gigantic segment down here with 105, and so this visualization is actually worse than a table would be. And so I want you to think about what are kind of some alternatives to visualizing this kind of data. And also, this isn't an isolated incident. This is like a common problem These are like various different high set diagrams that I found in scientific publications here. And so I want to like make this a little bit more tangible and give you an example with Simpsons characters. You have Lisa, Bart, Homer, and Mr. Burns, and then you have the sets. These are some characteristics about them. They go to school. They have like a gender, female or male. They work at the power plant. They are evil, and so on. And then you have attributes about those people, and like one attribute we'll be using is their age. And so I want you to create like 3 different designs for this data. But before I'll start a breakout groups to do that, I want to kind of like give you a couple of, because if you remember, we always talked about we need to design for tasks. We just like we have to know what is the data and what are the tasks that we need to design a visualization. And so here are some questions that you might want to ask. First is like, well, some hints, but first, like one thing that I want to emphasize is don't try to always show all individuals, because I've seen people always try to explicitly visualize every single character in these charts in the past, so don't always do that. Then ask, like try to answer questions easily with your visualization. What is the biggest intersections? Which sets make up an intersections? How big is an intersection, not only the biggest? And does it work for more than 4 sets? Is also something that I would like you to consider. Think of like if I have 6 or 7 sets, how would your visualization work? And now I would like you to work in groups. And we'll spend about like, well, this is a little bit generous here, what I have on the slides, but we'll spend like the good part of the rest of this lecture on this. I would like you to get to know the data in 5 minutes, then create 3 rapid prototypes in like about 10 minutes each, and then talk a little bit, like write up your 2 favorites in a Google Doc, and then upload this in your bonus Canvas Dropbox by 4 p.m. today. And then you will get this bonus point, and we'll discuss this briefly in class. And so now we'll share like detailed instructions here. Great, thanks, Shusha. So here you can see the detailed instruction. The actual data set I want you to consider is a little bit larger. We have kind of like the Lisa, Bart, Homer, Marge, Maggie, Barney, Mr. Burns, and Mo. These are our items. And then we have our sets. Are they in school or not? Do they have blue hair or not? Do they like Duff beer or not? Are they evil or not? Are they male or not? Do they work at the power plant or not? And then as an attribute, which we also want to visualize, is age. So for example, you should be able to, in your visualization, to show, is there like, what's the average age of people in the school versus the average age of people in the power plant? Or what's the average age of people who like Duff beer? These kinds of questions. And so here's some more guidelines. Before I start the breakout rooms, any comments, questions? There's multiple pages. Somebody missed this last time, but just make sure to look at both pages here. Okay, I'll start the breakout rooms, and I'll keep you in breakout rooms till like 10 minutes before the end of class. And then we'll come back and talk about some of these, about some of the designs. Okay, here we go.